Look around us today, and honestly, it feels like there is literally nothing modern machines can't do. I mean, we're watching artificial intelligence write flawless code, generate absolutely breathtaking art, and simulate entire worlds. It gives us this incredible, almost magical illusion of infinite computing power. But what if I told you that this power actually has an absolute, unbreakable ceiling? Welcome to this explainer where we're going to dive right into the ultimate boundaries of logic. It is kind of the fundamental question of our digital age, isn't it? Take a second and just ask yourself, given enough time, enough memory, and literally the fastest processors on the planet, can a computer solve any problem we throw at it? Is that illusion of infinite computing power actually real? Well, the answer is a hard, definitive no. It turns out there are some problems that, by the very laws of mathematics, are entirely impossible to solve. And I don't just mean impossible for your smartphone. I mean impossible for a supercomputer the size of the entire universe. And the guy who figured this out, he completely shattered our illusion of infinite computation and changed human understanding of logic forever. His name was Alan Turing. Section 1. The Turing Machine. So, to really wrap our heads around the limits of computation, we first kind of need to agree on what computation actually is. And for that, we've got to travel back to 1936 to a truly brilliant British mathematician and logician named Alan Turing. His ideas literally became the bedrock for all modern computers, algorithms, and AI. Now, in his big 1936 paper, Turing took this massively abstract concept and grounded it in something so relatable: a child doing math in a grid book. Think about it. A kid looks at one square at a time, follows a basic set of rules in their head, writes down a symbol, and moves to the next square. Turing realized, hey, any human calculation, no matter how wild or complex, can just be broken down into these incredibly simple, tiny steps. And then he did something amazing. He took that child's math grid and transformed it into a theoretical, imaginary machine. He flattened the 2D grid into this unbounded, one-dimensional tape. He swapped out the child's eyes and pencil for a reading head that scans just one cell at a time. And he replaced the kid's brain with a finite set of rigid rules. He called them states of mind. Today, we know this absolute game changer as the Turing machine. Which brings us to a super important concept in computer science: Turing completeness. Basically, if a system can simulate this universal Turing machine, it's Turing complete, meaning it has enough power to compute literally any algorithmic sequence. The takeaway here is that computation is a universal thing. The exact same mathematical principles that govern Turing's imaginary tape, well, they govern the electrical signals in a clunky vintage desktop, the tiny chips in your brand new phone, and, quite possibly, the firing of neurons in your own brain. Section 2. Birth of computer science. All right, so let's look at how this jumps from just being a cool math theory to the actual physical birth of modern hardware and software. Working alongside other pioneers like Alonzo Church, a profound concept emerged, known as the Church-Turing thesis. It basically says that everything humanly computable can be computed by a universal Turing machine. Bam! They mapped out the exact boundaries of what human logic and machines can actually pull off. Turing effectively proved that any computation can be represented as an algorithm, basically writing the genetic code for the whole future of computer science. But here's the thing. Turing wasn't just some theorist locked away in an ivory tower. His ideas had massive, earth-shattering real-world impact. During World War II, Turing actually put his theories into practice at Bletchley Park, building real physical machines to decode the German Enigma cipher. Historians estimate that the intelligence gathered by cracking those codes saved roughly 14 million lives, and ended the war 2 years early. And after the war, he used those exact same principles to design some of the very first electronic computers. He literally helped build the machines his math had predicted. How cool is that? Section 3. The Halting Problem. Okay, here is where we hit the massive plot twist of our story. While he was mapping out exactly what computers could do, Turing asked what seemed like a really weird question about software. Imagine you're writing a program. Could we build a universal master program that just looks at the code of any other program and reliably predicts whether it will actually finish running and give an answer, or just get stuck in a frozen infinite loop forever? We've all seen a computer freeze up, right? Because there's a huge, stark difference between computable sequences and uncomputable ones. Computable sequences come from circle-free machines, programs that just do their job, no drama, and output a result. But uncomputable sequences, that's when code gets stuck, it crashes, it hangs, it just loops endlessly. Turing wanted to know, Could an algorithm logically separate the good code from the endless loops before you even hit run? And the dramatic punchline of Turing's whole mathematical proof? There is fundamentally no way to tell. Seriously, if you try to build a machine to predict infinite loops, you can feed it a paradoxical program specifically designed to do the exact opposite of whatever your machine predicts. The logic literally eats itself. It's wild. This is famous today as the halting problem, and it proves definitively that some tasks are mathematically impossible for any algorithm to ever solve. Section 4. Limits of computation. Now, you have to understand, this discovery wasn't just some quirky little bug in early computer code. It was a total earthquake in the math world. Let's look at the massive fallout of this and what it actually means for the physical universe we live in. Back in 1928, the famous mathematician David Hilbert posed the Entscheidungs problem, the decision problem. He dreamt of a universal algorithm that could take any mathematical statement and definitively prove if it was true or false. Well, Turing's halting problem absolutely shattered Hilbert's dream. Because if you can't reliably predict if a machine will halt, then there can be no universal algorithm that proves every single mathematical truth. Some truths, they are just fundamentally unprovable by an algorithm. So what does this all mean for us? It means these hard boundaries are baked right into the fabric of reality. They aren't just an engineering glitch. Actually, scratch that. You can't fix the halting problem by throwing a faster microchip or a better cooling system at it. It doesn't work like that. To put it into perspective, the observable universe contains roughly 10 to the power of 80 atoms. Even if you somehow turned the entire cosmos into one giant glowing supercomputer, it would still be bound by Turing's limits. The uncomputable always remains uncomputable. Section 5. AI and the Turing test. Which leads us to a really fascinating philosophical leap. If machines are mathematically bound, if they hit this structural wall of logic, can they ever truly think like us? Could they be creative? Turing pondered this deeply, and in doing so, he essentially birthed the field of artificial intelligence. In 1950, he moved the whole debate from abstract math to practical, everyday conversation. He published a paper asking straight up, can machines think? And to test this empirically, he proposed the imitation game, which we all know today as the Turing test. Basically, a human evaluator has a text conversation with an unseen participant. If the human can't tell whether they're chatting with a person or a machine, well, Turing argued that machine has demonstrated true intelligence. Of course, our societal expectations for AI are constantly shifting. There's this fantastic cartoon by Tom Gauld that captures the evolution of the Turing test perfectly. It shows the test going from a machine just passing a simple chat, to feigning interest in sports, to arguing politics with your uncle, all the way to hosting a complex dinner party. It's hilarious, but it hits the nail on the head. As machines get smarter, we just keep moving the goalposts for what we consider real human thinking. And that really brings us to right now, today. We have these massive, large language models that are incredibly good at passing Turing's original test. But as our sourced reports point out, while modern AI algorithms beautifully mimic human intelligence in text, they often completely lack deep comprehension, real context recognition, and self-awareness. No matter how convincingly an AI chats with you, underneath the hood, it's still just a Turing machine, rigidly bound by the exact mathematical limits Alan Turing mapped out nearly a century ago. Turing's legacy is absolutely everywhere. I mean, his ideas form the entire backbone of modern programming, cryptography, AI, and even the wild future of quantum computing. But his work is also this deeply humbling reminder. Not everything in life can be solved just by adding more computing power. It leaves us with this really profound question to chew on. If our smartest machines are mathematically limited, will the deepest secrets of our universe forever remain uncomputable? Understanding these ultimate boundaries is exactly what makes computer science so unbelievably fascinating. If you want to keep exploring the absolute limits of reality, logic, and tech with us, make sure to subscribe to the Universe Code channel. We're here to take the most complex ideas in math and computer science and make them simple, clear, and super engaging. Thanks so much for joining me on this explainer, and I'll catch you in the next one.